Okay, this is the fourth Taylor polynomial example problem. We're going to do 10 of these. So once again, we're given the function sine x here, and we want to find the fourth degree Taylor polynomial of sine x centered at pi over 6. Then we want to use Taylor's inequality to find the maximum possible error we could get using Taylor's polynomial to approximate the function sine x, assuming that we're restricting the x values that we're going to input into the Taylor polynomial to be on this range. And then we want to, at the end, we want to compare the actual error, the actual r sub n of x over the interval to what we got using Taylor's inequality. Okay, now, looking at this, you see sine x, and you might think, well, okay, we might have some zero terms here, right? When we're going through the Taylor series, when we went through the Maclaurin series of sine x, we had every other term was a zero term, but that's not going to end up being the case here because we're not centered at 0. But we will have some problems coming up where some of the terms end up being 0, and that's not a big deal, but just remember that does make it a little more complicated as far as how to apply Taylor's inequality, and because then it makes the n's a little more complicated. What n are you putting into Taylor's inequality, things like that. So make sure you check out an example problem where some of the terms of the Taylor polynomial, we're skipping terms because there's some zero terms. Okay, because the Taylor polynomial, so here t sub 4, what does this mean? That we're summing the first 4 terms of the Taylor series of sine x centered at pi over 6? No, that's not what it means. It means we're going to sum however many non-zero terms we need until we get to the fourth order term, the x minus pi over 6 to the fourth. And then we'll stop there, and that'll be the Taylor polynomial. That's what the n means in regards to Taylor polynomials. It's a little bit different than just the classic S of n, partial sum. That's just, okay, we're summing the first n terms of the corresponding sequence, right? So every infinite sum or whatever, or sum it's a sequence, right? It's terms of a sequence, and you're summing those terms. Well, it's not quite that meaning with a Taylor polynomial. It's really the n's referring to the order of the polynomial. Okay, so to do this, we're going to start just like if we were building the Taylor series here. And so we make 2 columns, and then we write out f of x and its derivatives. So we've got sine x, f prime of x is cosine x, okay. Now we want to go at least to the fourth derivative, because we're going to need 4 derivatives to get to the fourth power, right? But we want to go at one past that because we're going to need this for Taylor's inequality. So this is cosine x. Now we want to come to the right column and plug the center point in to each of these. So, well, except for the fifth, that we can skip the fifth, plugging in the center point. So, okay, sine, we're in radian mode, sine of pi over 6 is 1/2. Okay. Cosine of pi over 6 is root 3 over 2. Okay, that should be all we need, because this is going to be minus 1/2. So, yeah, minus, okay. Okay, there we go. So there are the coefficients are of the Taylor series. It's the nth derivative evaluated at the center point over n factorial. This is the nth derivative evaluated at the center point. That's what this is. So now we want to get the actual c sub n coefficients. So we just need to divide these by n factorial. So we've got this divided by 0 factorial, this divided by 1 factorial, this divided by 2 factorial, this divided by 3 factorial, and then this divided by 4 factorial. 4 factorial is 24. 24 times 2 is 48. Okay, so now we can write out we've got the coefficients for each of the first, this is going to be the first 5 terms, but we're going to the fourth order. So, okay, sine of x is approximately equal to this t sub 4 of x, which is equal to what? Okay, 1/2 times x minus a to the 0 is just 1/2 plus root 3 over 2 times x minus pi over 6 to the first minus 1/4 times x minus pi over 6 squared minus root 3 over 6 times x minus pi over 6 cubed plus 1 over 48 times x minus pi over 6 to the fourth. Okay, let's see. Here, this was over 3 factorial. Okay, this is over 2 factorial. This is over 3 factorial. 3 factorial is 6, but 6 times 2 is 12. All right. Okay, there we go. Okay. So there we go. There is the Taylor polynomial, the fourth order Taylor polynomial. So now let's do the error estimation. So, okay, what we're looking for is, so we know that the sine of x is equal to the Taylor series, right? What this is equal to t sub, we're doing t sub 4 of x plus r sub 4 of x, right? We're trying to get an estimate on how big the largest this can be. So we want to plug in n is equal to 4 into Taylor's inequality. And again, if we had 0 terms that we skipped to make Taylor's polynomial, this gets a little more confusing on what n to put in. But we didn't have any 0 terms. Every term was non-zero, so this is t sub 4, so we want r sub 4. So we're going to plug n is equal to 4 into here. So we need to get so we know that a is equal to pi over 6. We know n is equal to 4. We know d here, we're going to be applying Taylor's inequality over a restricted interval, or a restricted distance away from the center point. That distance is, let's see, so x is, pi over 6, it's 1/6 above and below the center point. D is, or not, pi over 6 above and below the center point. Or no, it's 1/6. Yeah, pi over 6 above or below the center point. So we know D here is pi over 6. That's what we're applying Taylor's inequality for. So we've got everything we need, except we need the capital M. How do we get the capital M? We come up here. We want to take the absolute value of the n plus 1th derivative of the function, and is there some number, one number, that's greater than or equal to all of the other values of the function on this interval here? then that's going to be capital M. And this seems complicated. Like I always was intimidated by Taylor's inequality. This is really easy what they're asking here. As long as you have the information, like, we have D, we know, this is a little bit harder for proving a function is equal to its Taylor series because it's a little more ambiguous. We kind of don't know. D could be anything, but here, this is just what we did in chapter 4, the finding the maximum value of a function over an interval. That's what this is. Find the maximum value of this function here, the absolute value of the n+1th derivative of x over this interval. Okay, so what's the n+1th derivative? Here it is, cosine x. Well, this is actually, okay, because n is equal to 4. So the absolute value of the n+1 derivative of x is the absolute value of cosine x. Okay, is this less, what is this less than or equal to? Well, we know it's going to be 1, right? This is what's nice with Taylor's inequality. It works out really nicely with sine and cosine. Okay, and it's really for all. D doesn't matter here. For all x, this is true. So I don't even need to put for absolute value of x minus a is less than or equal to d, to pi over 6. Okay, so this is m. There it is. There's m. So, okay, now that we have m, we can get what we need. We want this. We want r sub 4 of x, the absolute value of it. We want a ceiling for it. We can't get the exact value with Taylor's inequality, or else then we know the actual function. There'd be no, this would all be pointless, right? So, okay, n+1 is 5, so 5 factorial, and then we know it's x minus pi over 6 to the n+1 is 5, and this is actually for all x. It doesn't, the interval doesn't even matter. So, okay, 5 factorial is 120. So, okay. So there it is. There's at least the initial part. Okay, so it depends on the x we pick, right? This upper limit on the remainder depends on the x we pick. So if we want to just get one single number that we can apply in general to answer this question, well, let's just pick the x that results in the largest value here. That's going to be either of the endpoints. Every time, this is going to be just pick an endpoint. It's going to be the radius. Just plug in the radius here. It doesn't positive or negative. You could take the absolute value. So this is going to be pi over 6. Is that right? Let me make sure I'm not going crazy here. So pi over 6 plus pi over 6 is 2 pi over 6. That's pi over 3. Yeah. Okay. So, okay. We've got, if we plug that in, we've got, so, all right. Pi over 6, like it wouldn't be x is equal to pi over 6. It would be pi over 3 or 0. That would be the x that results in the largest value under here, which would end up being pi over 6. So pi over 6 to the 5th divided by 120, 0.000328. And there we go. There it is. It's this r sub 4 of x. You can pick any x value you want within the interval and plug it in. And you're going to end up, what are you going to get? You're going to have the function's going to be equal to something, sine of x. Then the Taylor polynomial is going to be equal to something, That's t sub 4 of x that actually plugged in. But then r sub 4 of x is also going to be equal to something, but we don't know what it is. But we can say that no matter what x we plug in, if it's in this range, no matter what x we plug in, it's never going to be bigger than this, r sub 4, okay? Now, we do know the function, right? We know sine of x, so we actually could calculate r sub 4 exactly. We know what the function is, and that's what we're going to do next. We're going to actually graph the actual r sub 4 because we know that the absolute value of r sub 4 of x is equal to the function, so sine of x minus this. So we can actually graph the exact r sub 4 of x. So you might wonder, well, what's the point of the Taylor inequality? This is all just for illustration. It depends on the application. You might not be able to get r sub 4. It might be too difficult. So you definitely this is about learning how to use Taylor's inequality. Okay, so now let's go ahead and I'm going to plug into Desmos sine x minus all of this. Okay, so I plugged in sine x minus all of this into Desmos, and there you go. So pi over 6 is around 0.5, pi over 3 is around 1.0 something, but then at 0 it's higher than that. So here's looks like about pi over 3, but then the highest point looks to be at x is equal to 0. And the reason is because you might say, well, wait a minute, we could have chose either of the endpoints whenever we plug the endpoint into the absolute value of x minus a to the fourth. Yeah, that's true. But then when you factor in the combination of the capital M, the worst case scenario would be if you're plugging in x is equal to 0. And it's 0.00003 would be the error. Or no, 0.0003. And so it's just slightly better than this. So not bad. Taylor's inequality did well.